All right, so anyways, let's just start off. So sequences. All right, so definition. What is a sequence? Here we go. Right, so here we go. So an infinite sequence, so we're just gonna be talking about infinite sequences. An infinite sequence, so that's what I'm defining, so I'll underline it, is an ordered list of real numbers. Ordered list of real numbers. So it will look like this. So they're going to be inside of a set. It's going to be like A1, A2, A3, A4, dot, 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 forever. Okay, so here, A1, A2, A3, A4, A5, A6, and so on to infinity, each of those is a real number. Okay, so it's just an ordered list of real numbers. Okay, here is an example. Here's an example of a sequence. How about this? 2, 4, 6, 8, 10, and so on forever. That is a sequence. Okay, and maybe you see kind of the rule or the pattern for this sequence. How was it generated? But we're going to get to that. But so far, this is just a sequence. It's an ordered list of real numbers, and it's infinitely long. So the dot, dot, dot here, by the way, this represents infinity, so to speak. It's everything that comes after 10 in the sequence. So it's a little hard to believe. Maybe it's like you kind of have to imagine it, but this dot, dot, dot is supposed to represent an infinite list of numbers. All right. So hopefully you guys can believe that. Okay, so just a quick notation thing. How do we denote these guys? We denote a sequence. Sorry. We denote a sequence by, okay, so how do I just, what's a symbol for a sequence? So you open up these curly braces and you put a subscript n. That's one way to do it, or a subscript n, and on the side of the right curly brace, you do n equals 1, and then infinity on top. All right, so that's the notation for a sequence. Okay, and now just some more definitions. So this subscript here, that has a special name. So that n, so the subscript n is called, so that has a name, and it's called the index. Okay, that subscript n is called the index. And one more piece of terminology: each number a sub n is called the nth term of the sequence. Okay. So for example, a subscript 1, a subscript 1 is the first term of the sequence. Okay, and similarly, a subscript 7, a sub 7 is the 7th term of the sequence. All right, so you look up here, A1, A2, A3, A4, first term, second term, third term, fourth term. Okay, so that's kind of how that works. So I just need some language. I just need to tell you guys the language I'll be using when I describe sequences. All right, so any questions so far?
What does n equals 1 mean?
Right, so that means that the subscript that we start with, the first term, it will be 1.
So in theory, if we started at 2, it'd be n equals 2.
Right. So if for whatever reason, which you can do, if you wanted your sequence to start at n equals 2, so it would be A2, A3, dot, 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 that would be notated as A sub n, and on the right side, you would have n equals 2 to infinity.
Thank you.
Yeah, so you can do that. It's just not conventional. Conventionally and historically, you start a sequence with n equals 1. But this is absolutely allowable. So, very good. All righty. So
the infinity as the superscript, what does that mean at the very
right,
top?
the infinity as a superscript is just supposed to denote that the sequence has infinitely many terms. This is not a finite list, and that's represented with this dot, dot, dot.
Got it.
However, there are finite sequences. You know, surely you could have a finite sequence, but we're going to be dealing with just infinite ones. Okay. All right. Good. Okay. So sequences, they're going to come in 2 flavors, or in 2 styles. So sequences come in 2 flavors. And the 2 flavors are explicit formulas or defined by a recursive formula. All right, so we're going to be I will define both types and give examples of both types. So if you're into computer science and like coding, recursive formula, that kind of has to do with something called recursion, which is a concept in computer science and coding. So if you're familiar with that term, recursion, this recursive formula will make a lot of, you'll see the similarities between recursion and recursive formula. All right, so let's just talk about explicit formulas first. So here we go. So this is called explicitly defined sequences. Okay, so this is basically just when a sequence has an explicit formula. All right, I can plug in n and it will give me the nth term. That's the intuition. But here's just the formal, and here's just the formal definition. Okay, so here we go. A sequence is defined by an explicit formula if the nth term, a sub n, equals f evaluated at n, okay? And I need to tell you what f is, where f is a function whose domain is the positive whole numbers, whose domain is this set, 1, 2, 3, 4, 5, and so on. Okay, so basically each term of the sequence is given by a function. So how do I get the nth term? I get the nth term by plugging in n into this function f. So if I want the 7th term of this sequence, a sub 7, I'll just evaluate this function f at the value 7. All right.
And this is for all real numbers?
Is this for all real numbers? You mean all...
Like negatives, infinity.
Are you talking about the inputs for f? Are you talking about the
Yes.
input?
Yeah, that, yeah.
Well, no, because f is a function whose domain is 1, 2, 3, 4, 5, and so on. So f's domain does not contain negative numbers.
0 or no? None of that.
Usually not, but it can. But in our
Okay.
case, no. Okay, so the only permissible values to plug into f are 1, 2, 3, and so on. No negative numbers, no fractions, no irrational numbers. Okay, so obviously I'm going to give you guys some examples. So just quickly, in other words, the nth term is given by evaluating this function f of x at what? At x equals n. All right. So it's explicitly defined. I have a function that will just generate terms of the sequence depending on which n I plug in. Okay, so example. This is where things will hopefully become clear. The sequence negative 3n plus 8 is explicitly defined. Okay, so what's the function here? So look at the definition of what it means for a sequence to be explicitly defined. You need a function, okay? And the function is just simply this. It's that. That's the function, okay? It's literally, it's negative 3n plus 8. So here, f of n is negative 3n plus 8. Okay, so let's list the first 4 terms of this sequence. Okay, I would just like to list A1, A2, A3, and A4. Okay, good. So let's start with A1. So this is the case when n equals 1. A1 equals. So A1 just means I go to the expression negative 3n plus 8 and I plug in n equals 1. That will be the first term. So it's negative 3 times n, but n is 1, plus 8. And this is 5. So that's the first term of the sequence. It's 5. All right, how about n equals 2? Same story. So a sub 2 is obtained by plugging in n equals 2 into this function. So it's negative 3 times 2 plus 8. And what is this? This is negative 6 plus 8, so it should be positive 2. Yeah. Yep. All right, let's just keep going with this game here. So a sub 3, this is the result of plugging in n equals 3. So what do I have? I have negative 9 plus 8, which is negative 1. And n equals 4. A sub 4. So a sub 4 is the 4th term of the sequence. You just plug in n equals 4. So what is this? This is negative 7. All right, so here's what's changing here. It's just the input. So I'm plugging in 1, I'm plugging in 2, I'm plugging in 3, plugging in 4. So that's really, that's what you do to get terms of the sequence. So the sequence looks like this. If you want to write it out in its list form. So first term is 5, second term is 2, third term negative 1, fourth term negative 7, and now you just ought to put this dot, dot, dot here to represent that there are infinitely many more terms that come after negative 7.
Isn't it negative 4 for n equals 4?
Negative 12 plus 8. Yes. Yeah, it is. Let's see. Yes, it is negative 4.
Cool.
Yeah, thank
Just
you.
making sure I didn't miss anything.
Yeah, no, definitely. Yeah. Excuse me. Let me just change that in my notes very quickly. Yeah. Yeah. I had a feeling that sounded That sounded weird. Yes, so that will be -4, absolutely. Okay, and remember, these numbers I have written here is not every term in the sequence. There are infinitely many. You know, when you plug in n equals 5, n equals 6, n equals 7, those are all members of this sequence, but it's not really feasible, or it's not even possible to list all of them out, okay? You need an infinite amount of time, memory, and energy to list out every term of the sequence. It can't be done. But, you know, we just put this ... here to imagine it, okay? All right, so any questions? Okay, good. Let's do another example of an explicitly defined sequence. Okay, how about this guy? So this is a very famous kind of sequence, it's used a lot. So the sequence is -1 to the nth power. Okay, and I'm going to put in that notation here. It's from n equals 1 to infinity. Okay, good. Let's list again the first 4 terms. Okay, a sub 1. A sub 1 is obtained by plugging in n equals 1 into the sequence. So it's -1 to the first power, which is -1. Very good. How about a sub 2? Well, that's just a result of plugging in n equals 2. So I plug in 2 for that exponent n. Well, -1 to the second power is +1. A sub 3. That's plugging in n equals 3, so it's -1 to the third power, which is -1. Okay, negative number raised to an odd power is still negative. And a sub 4. -1 to the fourth power, that will be +1. Okay, so you can see the behavior of this sequence. It will just switch between -1 and 1. Okay, that's the behavior. Just bounces from -1 to 1. That's all the sequence does. Okay, so now let me just list this sequence in its list form. So it looks like -1, 1, -1, 1. Well, we know it keeps repeating like that, so it's -1, 1, -1, 1. Do that for however long you like, and then just make sure you put 3 dots at the end. Okay. All right, so just a quick piece of terminology. This is an example of an alternating sequence. Okay. The reason why it's called that is because the sign, the positive and negative sign is alternating between the two. Pretty good. All right, so any questions about this?
Could you explain where you said that alternating sequence?
Yeah, so this is just something you would call an alternating sequence, and that's because the plus and negative sign are alternating between one term's negative, one term's positive, next term's negative, next term's positive. So that's the alternating thing. Okay, so here is something different. So now what I did before is I gave you the explicit formula and then we listed terms of the sequence. How about we go the other way around? I give you the sequence and I shall ask you to give me an explicit formula. Okay, so this can be kind of fun sometimes. So example, find an explicit formula for the sequence. So I'm going to give you a sequence in a list. So the sequence is 1/2, 2 over 3, 3 over 4, 4 over 5, and so on forever. Okay, so I need a function such that when I plug in n equals 1, I get a half. I need a function such that when I plug in n equals 2, I get 2/3. So do you see kind of the game we're playing here? When n equals 3, I should get 3/4. And when n equals 4, I should get 4/5. So does anyone see what function will give me these desired sequence terms? So what's an explicit formula here for a sub n? Okay, well, here's a hint. The numerators of all these fractions, they're exactly what n is, and the denominators are, how are they related to n?
What they're multiplied by? Maybe? No.
Not
Times 2.
exactly. So I see.
Is it okay? Sorry. Is it n over n plus 1?
Yes, so that is the formula. So let me explain why. So I have n equals 1, and I need a function such that when I plug in 1, I get 1/2. So I need that f of 1 is 1 over 2. I also need that f of 2 is 2 over 3. I need that f of 3 is 3 over 4. So you can see that the input should match the numerator. Okay, so I definitely need f of n. In the numerator of it, I need n. Okay, and the denominators of all these guys are just one more than what n is. So you divide by n plus 1. Okay, so I hope that's kind of, you can see that now. And now you can see if I plug in 1, 2, 3, 4, I'll get back the sequence I listed out in the beginning. All right, so yeah, so this is how you could put your answer like this, or you could just write a sub n equals n over n plus 1. That works too. So these are both acceptable final answers. All right, so I hope that's okay. Just if you want me to explain it more, just let me know. All right, so you'll get practice on this on the last homework. All right, yeah, I forgot to say, homework 12 will be available probably tomorrow. I'm still in the process of writing it, so just be on the lookout for that. And that'll be due Thursday, a week from today. Okay, next, recursively defined sequences. Let's talk about that. Okay, so definition, of course. Okay, let's see, can I type this? Okay. All right, so a recursively defined sequence is a sequence where one or more terms are given explicitly and subsequent terms that come after that, are defined in terms of earlier sequence terms. Okay. All right, so let me just go and underline what we're defining here. We're defining this recursively defined sequence. Okay, so this is something that's best illustrated just with a concrete example. Okay, so essentially, I give you the first the first term or the first two terms usually, and then the next terms will be generated using using the previous guys, the previous terms. All right, so this is what it looks like in practice. So a sub 1 equals 3, and a sub n equals 2 times a sub n minus 1 minus 1. Okay? So here, so let's look how this parallels with the definition. So one or more terms are given explicitly. That's this piece. I'm telling you explicitly, a sub 1 is 3. And then subsequent terms are defined in terms of earlier sequence terms, and that's this piece right here. Okay, so let me explain what this means here. Okay, so I'm basically just going to write what I just said. So here we are given that the first term is a sub 1 equals 3, and the nth term is obtained by multiplying the previous term by 2 and then subtracting 1. Okay, so previous term, that's a sub n minus 1. That's the term that comes before the nth term. All right, so let's start listing out some of these. So n equals 1. That corresponds to a sub 1. And we're given that that's 3. So no work to be done on the first term here. Okay, n equals 2 is where we have to start using this recursive formula. Okay, so a sub 2. Okay, by definition, it will be 2 times a sub n minus 1. So if n is 2, then n minus 2 will be 1. So it's 2 times a sub 1 minus 1. And we can get this value because we know what a sub 1 is. It's 3. So this is 2 times 3 minus 1. So that's where that goes. And this is 5. Okay. Let's keep going. Let's do the third and fourth term. So I have n equals 3. So a sub 3. Okay, the formula tells us I multiplied the previous term by 2. So the previous term from a3 will be a sub 2, and then I subtract 1. Well, this is 2 times a sub 2, and look, we already have a sub 2. It's 5. We got it from our computation before. So it's 2 times 5 minus 1, which is 9. All right, and let's do the fourth term. So this will be a sub 4. This is given by 2 times a sub 3, the previous term, minus 1. So I do 2 times the previous term, which is a3. We got a3. It's 9, so you plug that in. It's 2 times 9 minus 1. So this is 18 minus 1, which is 17. All right, so any questions, confusions on how I'm obtaining these terms? You need to look at the previous term to get these terms. Okay, you use the previous term to generate the next term.
Would we ever run into an issue where we're not given the previous term?
No, because then you're kind of at a loss. You don't have enough information. So
Yeah.
no, definitely not. Good. So we're going to do another example, a very famous example, which maybe you've heard of at some point. So this is called the Fibonacci sequence. Okay, so a very, very famous, recursively defined sequence is the Fibonacci sequence. Okay, so you can't talk about recursively defined formulas and not mention this sequence. Okay, it's probably the most famous one. And so what's interesting about this sequence, I probably should have grabbed some pictures, but you see kind of the sequence manifest itself in like nature, like in like the petals of a flower and in some artwork. So it has some nice, pleasant real life applications. It shows up in nature, which is pretty interesting. Okay. Okay, so what is the sequence? Okay, so I need to tell you the A sub 1 is 0 and A sub 2 is 1. Okay, so this is the part of the definition where I give you terms explicitly. I'm telling you, the first term is 0, the second term is 1. Now I give you the formula to generate the rest with, okay, A sub n. Okay, so you take the sum of the previous two terms. So it's A sub n minus 1 plus A sub n minus 2. Okay, so you just take the sum of the two previous terms, and that's your nth term. All right, so let's get at this a little bit. So n equals 1. Well, that's A sub 1, and that was given to us already as 0, so no computation needed there. How about n equals 2? This is A sub 2. Again, A sub 2 was just given to us explicitly, so no computation. We were given the fact that A sub 2 is 1. So no other work needed there. N equals 3. Okay, so A sub 3, this formula right here tells us I need to add together A sub 2 plus A sub 1. So this is A sub 2 plus A sub 1. You take the sum of the previous two terms. Okay, good. And what's great is that we have A sub 2 and A sub 1. They're right here. So it's 1 plus 0. And that's 1. Okay, so A sub 3 is 1. All right, let's do another. N equals 4. This is A sub 5. So the formula tells us I need to add together the two previous terms. So it's A sub 4. Where did I mess up? Oh, yeah. Oh, sorry. Yeah, A sub 4. I don't know why I wrote 5. A sub 4. Okay. A sub 4 is equal to the sum of the two previous terms. So it's A sub 3 plus A sub 2. And we have these. A sub 3 is 1, and A sub 2 is 1. So this is 2. Let's do one more. N equals 5. This is A sub 5. So this will be A sub 4 plus A sub 3, the two previous terms. A sub 4 we got, it's 2, and A sub 3 is 1. So it's 2 plus 1, which is 3. Okay. So I hope everyone's okay with how I'm getting terms of this sequence. Okay, just let me know. Essentially, you just have to add together the two terms that come before the nth term. That's how you get the nth term. All right, so I'll move on to arithmetic sequences if no one has any questions. Okay, next heading, arithmetic sequences. These are nice. Okay, I'm just going to type this. Definition. An arithmetic sequence is a sequence, first of all, such that the difference between any two consecutive terms is the same. Okay? So if I take any two terms that are next to each other, and I do the one that comes later minus the one before it, that's going to be the same number no matter which two consecutive pairs I pick. All right, so example. So here we go. So how about this? 3, 7, 11, 15, 19. So I need to ensure that the difference between any two consecutive terms is the same. Okay, so I do 19 minus 15, and that's 4. So I do this term minus its previous term, that's 4. I do 15 minus 11, that's this term minus its previous term, that's also 4, right? Then you do 11 minus 7, you check that pair, that's also 4. And finally, you do 7 minus 3, which is 4. Okay, so again, the difference between any two consecutive terms is the same. Okay, in this case, the difference is 4 between any two consecutive terms. So you need this number here to be the same. Okay, so we just have a piece of terminology. This number 4 here, it has a name. So the number 4 in the previous example is called the common difference, all right? That's the name we give to that common difference, and it's usually denoted with by, usually denoted by the letter D, lowercase d. Okay. So any questions here about why this guy is arithmetic?
Can it also be just the sum instead of the difference?
Yes. So be careful, not the sum between any two terms, because 7 plus 3 is 10, and 11 plus 7 is 18. But you need to add 4 to get to the next term. It's the same way of saying it, right? So to get from this term to this term, you add 4. To get from this term to this term, you add 4, and so on. So you can think of it as just adding the same number to get the next term. Okay, very good. Yeah. Okay, so what's really kind of nice and beautiful about arithmetic sequences is that we can actually come up with an explicit formula for a given one, okay? So the only data we have about it is that the difference between any two consecutive terms is the same, but we can get an explicit formula. All right, so let me show you guys this. This is really nice. So, yeah, I'm gonna start on the next page here. So we can actually come up with an explicit formula. For the nth term of an arithmetic okay, so here's the proof. All right, so this is really interesting. So here's the proof. So I'm just gonna kind of show you guys like the derivation of how you do this. So here we go. So first off, you start off by supposing that a sub n is an arithmetic sequence with common, so whenever I tell you something's an arithmetic sequence, I also need to tell you the piece of data, which is the common difference, with common difference d. Okay, so it's very general. This is not a concrete sequence, it's just given abstractly. Okay, so we have this arithmetic sequence and we know that the common difference is d. We would like to come up with a formula for the nth term. Okay, so we want a function f such that f of n is the nth term, just given this information. And we can actually do that. All right, so here we go. So then a2 minus a sub 1 equals. Okay, if I know that this is an arithmetic sequence with common difference d, that means that the difference between any two consecutive terms is d. So thus, can someone tell me what a2 minus a1 will be?
It would be D, right?
It would be d, exactly. This term comes right before a1, subtract them by definition, this will be d. Okay, good. So now solve this for a sub 2. So a2 is equal to a sub 1 plus d. Okay, so we just got a formula for a sub 2. Let's keep going now. Here's one, here's another. Okay, now let's do this again with a3 minus a2. Okay, these are consecutive terms. So when I take their difference, the result will be d. Okay, now solve the, well, actually, so now a sub 3 minus, you replace a2 with what we got for it up here. How cool is that? So it's a3 minus, well, a sub 2, we have a formula, it's a sub 1 plus d. So you replace that right there. And that's equal to d. All right, so I hope everyone sees. I replaced a sub 2 with its equivalent expression, a1 plus d. Good, so now you can distribute the minus sign here. This is a sub 3 minus a1 minus d is equal to d. Solve this for a3. You'll get a sub 3 is equal to a sub 1 plus 2d. All right, so just verify that. If I solve this guy for a3, I do get that. Okay, good. So we have an explicit formula for a3. Let's do one more, and then maybe you guys will see the general pattern. Let's do a sub 4 minus a sub 3. Okay, again, I'm taking the difference of two consecutive terms, so I know that this is going to be d. Okay, now I can replace a sub 3 with its expression that I got up here for it. A sub 3 is a1 plus 2d. So I sub that in right here. a1 plus 2d. Okay, this is a3. Good. Now solve this for a4. That's what you would like to do. So A4, so distribute the minus sign. Oh, sorry. So it's A4 minus A1 minus 2D equals D. Solve this for A4. This is A sub 4 is equal to A1 plus 3D. Okay. So I think now we may have enough evidence to see what the general nth term is. So general pattern, and I'll ask you guys to think about it for a second, and maybe someone can tell me. That would be cool. So a general pattern. The nth term is given by what? What do we see in common with all these formulas? So I have this number, I have 2D in A3, I have 3D in A4, I have A1 in all of them. So what may the nth term be given this evidence here of the first four terms? So we're trying to find general formula here. So all of them have A1 present. It's A1 plus D, A1 plus 2D, A1 plus 3D. So A sub n will be A1 plus something, okay? Now, in this case, the coefficient in front of D is 1 less than the subscript. Do you see that? A sub 4 has 3 as the subscript, has 3 as the coefficient. A sub 3 has 2 as the coefficient, okay? So if the subscript is n, what would the coefficient in front of D be if it's 1 less?
Just n minus d.
N minus
1.
N minus 1, right. There we go. So that's the formula. All right, so I was just trying to print out enough terms so that you would maybe see that it follows this general pattern here, okay? So the coefficient in front of D is always 1 less than the subscript. So look, the coefficient in front of D is 3, and the subscript is 4. So it's n minus 1. All right, so this is the formula. It's the first term plus n minus 1 times D. All right, so let's use this guy. So let an be arithmetic. When I say that, I just mean let an be an arithmetic sequence. Okay. Suppose a sub 1 equals 8, and the fourth term, a sub 4, equals 14. Given this info, find the fifth term, a sub 5. Okay, so this may seem like, wow, like how in the world can I do this? I have just the first term and the fourth term. But given this formula here, it's actually possible. Okay, so I want A5, right? So firstly, by the formula, meaning this general pattern I have here, this highlighted, A5 will be A sub 1 plus 4D. Okay, but we have A sub 1, so even better, A sub 5 is equal to 8 plus 4D. Okay, so in order to get A5, I just need to find D, okay? So you need to find D, because look, if I have D, Then I just plug it in, and I will get A5. Okay, how can I do that? I need to use this guy. A sub 4 is equal to 14. I need to use that. Okay, so A sub 4, firstly, it's equal to A sub 1 plus n minus 1 times d. Right, but n minus 1 is 3 here. So it's A1 plus 3d. Okay, and this is just by this formula up here when I plug in n equals 4. Okay, but we have a lot of this stuff. We have that A4 is 14, so that's the left side. A sub 1 we also have, which is 8. So 14 is equal to 8 plus 3d. And I can solve this guy for d. Okay, so you get that, so you subtract 8 from both sides, you get that 3d is equal to 6, and hence d is equal to 2. So we found d, and now we can plug it into the formula for a sub 5. So thus, a sub 5 is equal to 8 plus 4d. And we plug in now 2 for d. So it's 8 plus 4 times 2. So it went right here. D equals 2 went right there. And this is 8 plus 8, which is 16. All right, so it's a little bit of magic, maybe, but if you maybe look at this again, it'll be clearer, I hope. All right. Okay, so any questions?
We'll always be given the formula too, right?
Oh yeah, the formula, yeah, you'll have that definitely.
So we'll get the formula plus at least one term. And then, okay.
Yeah, you're always going to have enough information to solve it. And on the homework that I'm writing for this lecture, I print the formula on there too. So you'll have it. Yeah, let's do another example. So we just want to utilize this formula. We want to just have some practice using this. Okay. Example, write an explicit formula for 2, 12, 22, 32, 42, and so on. Okay, so firstly, you need to verify that this is in fact an arithmetic sequence, okay? So firstly, verify this is arithmetic with d equals, okay, what's the common difference here? Oh, if I do 42 minus 32, it's 10. If I do 32 minus 22, it's 10, and so on. So it looks like here that the common difference, d, is 10. Good. So it's arithmetic. So we can use our formula for an arithmetic sequence. Okay. Also, a sub 1, which is the first term, is 2. So thus, using the formula a sub n is equal to a sub 1 plus n minus 1 times d, we just plug this into this formula. Plug in. Okay, so a sub 1 is equal to, a sub n is equal to a sub 1, which is 2, plus n minus 1 stays, and d, I plug in 10. Okay, and now you can just simplify this. This is 2 plus, now you can distribute the 10 through. So this is 2 plus 10n minus 10. And now finish it off. This is 10n minus 8. Minus 8, not 18. Minus 8. All right, and that's the explicit formula, okay? All righty. So hopefully I'm not really hearing from anyone. I'm not sure if people are following me or not, but please let me know if anything's confusing. Okay, it's kind of tough to see if people are following what I'm doing.
No, it seems pretty self-explanatory. You're just plugging in things that are given.
Right, right. But like we needed to find D.
Yeah, it's just the difference.
Yeah. Exactly. All right, good. All right, so, all right, good. All right, so let's move on now to the final type of sequence we'll talk about. Probably more important than arithmetic sequence is geometric sequences. This will be how we'll end. Geometric sequences. Okay, so definition.
Just real quick, for every arithmetic sequence, it's always going to be a subscript n, a1 plus n minus 1 times d every time, right?
Yes, meaning that the nth term is given by this formula. So if I want the 500th term of an arithmetic sequence, I plug in n equals 500 into this formula. So, oh yeah, and the first term will be given to you. Or yeah, or you'll be able to find it. So a sub 500 will be a sub 1 plus 499 times d.
And d would be given to us probably too, right?
Yes, d, or there is going to be some way to figure it out. Absolutely. Yeah, thank you. All right, so geometric sequence. So let me just explain quickly. So this is, I think, a little more important and more popular than arithmetic sequence. So this is going to come up in calculus a lot. So let's talk about this. So a geometric sequence is a sequence in which any term divided by its previous term is the same. So for an arithmetic sequence, when you subtracted a term by its previous term, it was the same, no matter what pair you chose. Here, very similarly, instead of subtraction, you do division. So you divide any two pair of consecutive terms, it will be the same. All right, so there is some parallel to an arithmetic sequence. You replace the subtraction with division. Okay, all right, so an example is definitely in order. How about this guy? So how about this sequence? 1, 2, 4, 8, 16, ... Okay. So you need to divide each term by its previous term. So you do 16 divided by 8, which is 2. You do 8 divided by 4, which is 2. You do 4 divided by 2, which is 2. And you do 2 divided by 1, which is 2. So it is geometric. Okay, the reason why it's geometric is because I got this number 2 when I divided any term by its previous term. Okay, good. Definition. So again, we do have a piece of terminology for this number 2. So the number 2 in the previous example is called the common ratio. And is usually denoted by R. Okay, usually use the letter R. Okay, so example again. How about this guy? 3, 9, 27, 81, dot, dot, dot. This is geometric with R equals what? So would someone like to tell me what's the common ratio here? What do you get when you divide each term by its previous term?
3.
Yes, 3. Thank you, Kristen. Yeah, it's 3 because just quite simply, 81 divided by 27, 3, 27 divided by 9 is 3, and so on. All right, very good. Very good. And equivalently, you can do the next term is obtained by multiplying the previous term by 3. So to get from 3 to 9, you multiply by 3. Get from 9 to 27, you multiply by 3. You can think of it in terms of multiplication if you like. All right, very cool. All right, so again, we do have an explicit formula for a geometric sequence. Okay, so this is also really nice. All right, so we're almost done for tonight. Let's just get this formula in. We'll do an example with the formula. We'll be finished. So explicit formula for a geometric Okay, so I'm going to do a similar type of derivation or proof, like when I got the explicit formula for an arithmetic sequence. So the setup is this. So you let A sub n be geometric with common ratio R. Good. So I would like to get at a formula for A sub n, the nth term. Okay, good. So firstly, A sub 2 divided by A sub 1. What should this be? If we know that it's geometric, I know the common ratios are, what should A sub 2 divided by A sub 1 be? The division of its term by its previous term. Does anyone see?
I think it's A sub 3, right?
Not A sub 3. So I know that when I divide a term by its previous term, it's going to be the common ratio R. That's the definition of common ratio. So this would be R. And then this will imply, if I solve this for A2, A sub 2 is equal to A1 times R. Okay, so that's that. Okay, now let's do the same thing with A sub 3 divided by A sub 2. Since I'm dividing two consecutive terms, this A sub 3 divided by A sub 2 is definitely R. But I have a formula already for A sub 2. It's this highlighted guy, so I plug that in. So this is A sub 3 divided by A1 times R is equal to R. All right, so I plugged in the formula for A sub 2. Now solve this for A3, you get that this is equal to A1 times R squared. All right, let's do this one more time. A sub 4 divided by A sub 3. Okay, I'm dividing two consecutive terms, so this division is definitely equal to r. But again, I have a formula for a sub 3 already, so I sub that in for a3. Okay, a3 is equal to a1 times r squared. And this is equal to r. All right, so I'm just substituting in our formula for a3, and it's right here. Good, now solve this for a4. A sub 4 will be a1 times r to the third power. All right, so we kind of, I think maybe now we have enough evidence to see what the general formula should be. So general formula. Okay, so I want a formula for the nth term. Does anyone see what it could possibly be? Examining our test cases here. So what's present in all of these is a1, a1r squared, a1r cubed. So it ought to be a1 times something.
A1 R n minus 1. That might be wrong.
Yeah, no, that's good. So it just confirm with me that you said a sub 1 times r to the n minus 1 power.
This one. Yes.
Yeah, that's exactly right. Because if you look at the fourth term, the power of r is 1 less than that, it's 3. You look at the third term, the power of r is 1 less than that, 2. So look at the nth term, the power of r ought to be 1 less than n, which is n minus 1. All right, so that's the formula. So I'm just going to rewrite it because I wrote it a little sloppy here. So it's a1 times r to the n minus 1. So the only thing that's being raised to the n minus 1 power is r, not a1. All right.
So I just want to ask a quick question. So n minus 1 pretty much can be interpreted as the previous number, right?
Absolutely, yes. Definitely. All right, good. So I just have two quick practice problems that uses this formula, and then we'll be done. All right, so example. Suppose firstly that the sequence an is geometric. Suppose that a sub 1 is equal to 3 and a sub 4 is equal to 24. And you would like to find a sub 2. Okay, so firstly, by the formula, a sub 2 is equal to a sub 1 times r to the first power. A sub 2 is equal to a1 times r to the first power. So I'm using this formula with n, plugging in n equals 2. That's how I'm getting this. So that's by the formula with n equals 2. Okay, but what's nice is that we have a sub 1. So this a sub 2 will be equal to 3 times r, because I'm given that a sub 1 is 3. Okay, almost done. We just need to find r. Okay, and then we can just plug it in to a sub 2. Okay, so we need to use this piece of information, the fact that a sub 4 is 24. Okay, so firstly, a sub 4 is equal to, in the formula, it's equal to a1 times r to the third. So that's by the formula. But on the other hand, I know that a sub 4 is equal to 24. So I can fill in this left side with 24. And I can also fill in a sub 1 with 3. So this is equal to 3 times r to the third power. All right, so I'm just plugging in the information that I know. I know a4 is 24, so I plug that in there. And I know that a sub 1 is 3, so I plug it in there. Now solve this for r. So you have that r cubed is equal to 8. Divide both sides by 3. And then take a cube root. You'll get that r is equal to 2. Okay, good, almost done. So thus, what did we want to find? A sub 2, right? Yeah, a sub 2 is equal to 3 times r. Well, we just figured out what r was. It's 2. So we plug that in for r. So a sub 2 is equal to 3 times 2, which is 6. Right. So that is completed. All right, last example for tonight. Again, we're going to use this formula here, this geometric sequence formula. All right, right. So I would like for you to write an explicit formula for this sequence. 2, 10, 50, 250, ... Okay, so we need to first see that this is a geometric sequence. So first verify it's geometric with common ratio. All right, so I just need to divide each term by its previous term, and I'll be able to figure out the common ratio. So 250 divided by 50 is 5. 50 divided by 10, also 5. 10 divided by 2, also 5. So we can say with much assurance that r is 5. Okay, very good. Also, a sub 1 is equal to 2. So, using that formula, a sub n is equal to a sub 1 times r to the n minus 1 power. I can just substitute in my information. R is 5, and a1 is 2. So substitute that into this formula. So a sub n is equal to 2 times r, a sub n is equal to 2 times 5 to the n minus 1 power. All right, so I just substitute in my values for a1 and r.